All right, great. We good now? All right, great. Thanks so much. Thanks to everybody who came in today to hear the talk in person, and thanks to everybody who made it online. So today I'm going to summarize some of the recent research that's been going on in my research group, which I've now dubbing this work computational habitability. I've listed here a lot of the students who have participated in this work over the last few years. This is actually not an exhaustive list of all the collaborators. For example, Tom Quinn is here. He helped out quite a bit. A lot of this work. Vicky Meadows online helped out a lot. But these are sort of the students I'm going to highlight here today. If I put everybody on, it would be an entire screen of names. So you might not have heard this term computational habitability before because I made it up pretty recently, but I think it's a pretty apt description of what we're trying to do. So I thought I'd just give you a definition of what I mean by this. I have two definitions for you. First, it is the numerical methods that enable the simulation of all the processes that affect a planet's or moon's ability to sustain liquid water. A second definition would be a software framework for calculating the probability that a specific planet or moon can, or will support liquid water. So I don't want to have you all think that this is a solved problem. This is an aspiration. These are aspirational goals. And of course, we're not the only people working on this. Nick in his thesis work is working on similar projects. David and Josh KT, who are in the room, are also working towards these goals. But I think this is a nice articulation of where I'm trying to go and what we're trying to accomplish in the group. So I'm going to try and touch on both of these in the next 25 minutes or so. So I'm going to start out by talking about goal number one, trying to simulate all the processes that affect water. As Nick mentioned, right, we're going to, as we start looking for these exoplanets, we're going to know almost nothing about them. But we do know that the laws of physics and chemistry have to apply. And so that's what we're trying to do, is kind of narrow down that possible range of types of planets that could be out there that we might be able to observe with some of these great new telescopes. So if you've seen any of my talks at all in the last few years, you've seen a slide that looks very much like this. This is basically, sometimes we call this diagram planets are hard, after Mark Clare, who coined that. I also like Suzanne Hawley's name for it, the habitability confusogram. But this is basically an attempt to collate all the different processes that might affect a planet's or moon's ability to support liquid water. In this case, specifically on the surface. When I put this slide together, it's almost been 12 years now since I did that. But I divided it up into these three broad categories of the effects of the star, the effects of the planetary system, and the planet itself. The planet, of course, can be divided further into the role of the atmosphere, the interior, and the surface, and as well as its dynamics, things like its rotation rate. So this is how I tend to think about this problem. It's how I've thought about it for years. And what I'm going to do first is kind of take you on a little tour of this map and just try and convince you, if you haven't already been convinced, that all of these aspects do in fact matter for planetary habitability. And along the way, we'll try and highlight some of the work of the fantastic students who have been working with me on this. So I'm going to start down here in the bottom left. If you can read that, that's the atmosphere. So we'll start out by talking about some of how the atmosphere can affect habitability. And in particular, I guess I want to move that so I don't cover up the students. So it's been has been completed by Laura Amaral, who is a student that I'm co-advising with Antigona Segura down at UNAM. That's the National University in Mexico City. And Laura has been looking at how do flares accelerate the process of water loss on exoplanets. And in particular, okay, there we go. Just how much does the high energy radiation, so in the X-ray and the ultraviolet, how does that speed up the process of water being lost from atmospheres? So these are some great figures that she put together in her paper that came out earlier this year that just sort of show schematically what's going on. Is that these high energy photons come in, they hit water molecules, break them apart, and then the hydrogen atoms often have enough energy to escape the planet. And sometimes they have enough energy to drag oxygen along with it. And so this is sort of the physical picture you should have in your head. We're not doing anything with the interior at this point. This is just what's going on in the atmosphere and the space. And I'll just call out what I say right there, that note that we have this funny unit that we use, TO, which stands for the amount of water in Earth's oceans today, or terrestrial oceans. So here's a result from her paper. So the colors here show basically the amount of water being lost. The top panel here shows the total amount if you include basically the quiescent evolution of a star, so when it's not flaring, as well as the role of flares. And then the second one is when we subtract out the quiescent evolution of the star. And so you can see that from the color bars that we're losing several Earth oceans of water. And this is for a specific case of a 3 Earth mass planet around about a 0.2 solar mass star. And this was the most severe case that she was able to uncover, where basically about 2 times the amount of water in Earth's ocean was removed solely by the high energy radiation from flares. And that accounted for about 45% or so of the total water loss from the system. So that's telling us that the flares do, in fact, accelerate the possible desiccation of planets around low mass stars. All right, I'm going to move on now because you're going to come fast and quick for you all. So, but just kind of a top level overview of the stuff that we're working on. Next, let's think about the interior. And this work is from Rudy Garcia, who is looking into the thermal and magnetic and volatile evolution of Venus. And in particular, he's trying to answer this science question of how did Venus arrive at its current state, assuming that it always had a stagnant lid. So the schematic for this is pretty complicated, so I'm going to walk you through it pretty quickly here. So there's still an atmospheric escape process that's very similar to what Lauda works on, where the star is evolving. But in this case, the atmosphere is a little more complicated. We're including carbon dioxide. We're including radiative transfer, but in a very simplified way, just basically a 2-component gray model, if you're familiar with what that means. There's outgassing now from the interior, which I haven't shown you yet, but there's outgassing that's pumping these molecules into the atmosphere, and the starlight can still photolyze the water and lead to hydrogen escape. Rudy's also put into a crust into the model now, where the crust evolves dynamically based on the local conditions. Carbon dioxide and oxygen can be absorbed at the surface. You can also see now some appearance of some radioactive symbols here. So there's radioactivity throughout the whole interior. Then we get down another layer into the mantle, where there's convection that's modulated by melting and the amount of water. There's still radiogenic decay in here that's heating the mantle. And then there's the crust can, as I said, it's dynamically evolving, so it can be subsumed into the mantle. And finally, there's the core. So we've gone all the way down to the bottom, where we have a potentially convecting core that can drive a geodynamo. There might be radioactivity in the core or not. We allow it in this case. And we also allow for the inner core to nucleate, which can also push energy into the mantle and drive the evolution of the planet. All right, so that's a lot, but you know what to say, planets are hard. That's just a quick schematic of it. And Rudy has taken this model and run with it, literally. He's run 800 or so trials that I'm going to show you right here. And what I'm showing you on the left are basically some simulations that he ran, which basically reproduce observations that we already have. So looking at the amount of water and CO2 in the atmosphere, as well as the internal magnetic field, which is non-existent on Venus. So the model is in fact reproducing Venus. And then on the right are some predictions, basically. So we can now take this model and start to predict sort of what we might see on Venus. And as you might know, there's a few missions that are now being planned to Venus. Some of them might be able to start to probe these sorts of parameters on Venus. And in terms of the broader goals of this research, right, this is now a validated model for Venus. And so we can now start to apply it to exoplanets with the hope that there's some realism there. And this is also, I want to make sure to point out that Josh KT has done a lot of work similar to this, although without the core, but he's got some other nice features in there as well. So there's definitely a lot of work being done locally to try and understand the evolution of Venus and how it applies to exoplanets. All right, moving on. Let's talk about the surface next. And in particular, we're going to talk about this work from Caitlin Wilhelm, who was an undergraduate in my group for many years. She was a pre-map student here, if you're familiar with that program we have at UW. And her research project was to look at the ice coverage of Earth-like exoplanets. And in particular, just looking more broadly at how does the properties of the planet and the star affect the likelihood that there is ice either covering the entire planet or partially covering a planet. So to perform these experiments, she used an energy balance model, which is just a one-dimensional climate model shown schematically here very crudely, where you have basically a 3-component surface that reflects different amounts of light based on whether there's ice or land or sea, and includes the ability for heat to be redistributed latitudinally. Caitlin performed an enormous number of simulations. I think there were 270,000 that are in this paper from earlier this year. Here's just sort of one result I don't have time to go into all of it, but basically this is where the ice coverage was on the planet, like that was Earth-like, and I really do mean Earth-like in this case. Basically just a model that reproduces the Earth, but now pushed into these different parameter spaces, where we looked at the installation. So this is the amount of flux that's hitting the planet, and on the y-axis there, and then the obliquities on the x-axis, and the different colors you can see there correspond to different final states after 1 million years. So this is no orbital evolution or anything like that, but just sort of mapping out where are the boundaries between some different possible climate states. And you can see that the Earth thankfully lands there in the polar cap region. But note also that there's this interesting light blue region where there's ice belts. And so pretty fascinating. And these have been predicted, of course, before, but I think this was the first study that really mapped out where the ice belts are. And I think just one curiosity that we realized when we worked on this is that the planet formation models predict obliquities will tend to form near 90 degrees. And when you kind of work through the math of this, it suggests that ice belts are going to be twice as likely as ice caps out there in the universe. So a great thing to predict with LUVEX. Hopefully that'll come along. I don't know how it affects your models at all. I don't think at all, but nonetheless, it could imprint something into the photometric signal of some of these planets that are hopefully going to be observed in the near future. Don't have time to talk about it, but we also looked a lot into the stability of these ice belts by varying the eccentricities and obliquities and precession angles, which is the angle orthogonal to the obliquity. And this prediction is basically borne out from that even when you include perturbations that might be due to multiplicity in the system, you still get ice belts that are stable. You can also get really crazy chaotic climates. Happy to talk about that with anybody who's interested. And you can also check out this paper. Could be a lot of fun climates out there in the galaxy. All right, moving on. Let's move up here to the planetary system. So this is kind of getting closer to my realm. And in fact, this is where I'm going to show you some work that I did. So the picture is probably taken from about when I did this work in 2015. But looking now at the role of the planetary system, some of you may have seen this before as I've shown this, as it's a bit older result, but fits in nicely with this talk. And the question I wanted to ask here was just how extreme can the evolution of planetary orbits be? And so kind of stumbled on it was something I've been looking for probably 15 years when I finally found it. And I want you to consider this case right here. This is a little diagram that was put together by the folks at Universe Sandbox. And what this shows is sort of a schematic, it's just a cartoon of the system where there's an Earth-like planet that's orbiting a sun-like star. It's not to scale, but wanted to highlight the planets here. And then there's a Neptune-mass planet that's in a 3-to-1 motion exterior to the Earth-like planet. So that means it's as the Earth goes around every 1 year, the Neptune-mass planet goes around every 3 years. But unlike our solar system as well, I kicked up the inclinations and the eccentricities, but I made sure that they were in this resonance, this mean motion resonance. So I'm going to show you a little animation here of what this does. So the left is a top-down view of this planetary system, and the right is edge-on. Orange is, of course, the Earth-like planet, and green is the Neptune-like planet. The eccentricity and inclinations are there at the bottom, and those little tick marks on the left panel are the location of closest approach to the star. All right, so now I'm going to turn on gravity, and you can watch how planetary dynamics can torture a planet. So you can see that the eccentricity aperiodically approaches 1, meaning that it's basically just a plunging orbit, almost just a line. And at the same time, the inclination is moving around quite dramatically. And this simulation takes place over about 1 million years. But I can tell you that I was extremely nervous about this simulation, and I actually ran it to 10 billion years with multiple different methods. And this evolution is stable in the sense that it persists for 10 billion years. Now, the eccentricity reaching that high, it was actually got up to 0.999997, which actually sends it into the core of the sun. So this is not a self-consistent simulation, but I do think it proves that orbital dynamics can be as severe as you want. And I see Tom has seen what he wanted to see and is leaving the room. So seeing the orbital dynamics, time to move on. All right, we'll move on though to the next part of the talk. And we'll move over here to the stellar properties. And this is work that was led by David Graham, who was another undergraduate in my group who is now at the University of Heidelberg. And he looked into this question of circumbinary planets. How do circumbinary planets behave if the inner binary is evolving? And so when you have a binary star that are pretty tight orbits, tidal forces between the stars can actually cause their orbits to change over time, which would then cause a back reaction onto the planets. So schematically, this is what this looks like. Imagine you have these two stars. One is a 0.1 solar mass star, the other is half a solar mass. They're denoted by the red and the yellow there respectively. And then again, there's a little mascot planet for the talk, the Earth-like planet that's in a habitable orbit. It turns out that as the stars are evolving, they're contracting, which is causing them to spin up, but they're also losing matter through stellar winds, which causes them to slow down. And the tidal torques are causing them to either spin up or spin down, depending on their properties. So there's this really complicated angular momentum dance that goes on with these stars. But the long and the short of it is it causes the orbit to expand and to become more eccentric, and then over time circularize to just being, a smaller and circular orbit for the binary stars. And so the planet has to respond to all of this, and I've tried to sort of show that schematically, but maybe it works best in a plot. So here on the top panel is this is a figure from David's paper that came out last year, where we looked at the top panel shows you the installation again, where that first drop is due to basically stellar evolution. The low mass star in particular is getting much dimmer over time. And now the thickness of that line, though, is actually due to oscillations of the planet's orbit, right? So it's bobbing up and down in terms of semi-major axis and eccentricity, which are shown below. And so those orbital oscillations are causing that thickness that you can see is also changing quite a bit over time. The middle panel there is the semi-major axis of the planet, including a stability limit. So if the planet were to dip below that black line, it would be ejected from the system, but in this case it didn't. And you can see there that it does have sort of this weird envelope behavior. And the same with the eccentricity, it increases and then it drops again. And this is typical of the energy is being damped from the system, right? Because the binary star is losing energy, and so that's causing this damping over time. So long-term Milankovitch cycles are possible on these circumbinary planets if the binary star is tidally evolving. All right, the last stop on our tour of this diagram is to come over here to planetary dynamics. And in particular, we're going to now look at another system of interest, which is called Teegarden over time. This is work from Lion Gez, who is another undergraduate here, but is now a graduate student at the University of St. Andrews in Scotland. And they looked at this question of how do stellar tides and planet-planet perturbations combine to work together to affect the planet's rotational properties. So in Teegarden star, this is sort of the picture the mental model you should have here is that it's a 0.09 solar mass star, or actually, excuse me, 0.08 solar mass star. It's got two planets that are probably in the habitable zone. They probably formed with some eccentricity, and again, they probably formed with obliquities near 90 degrees. So in this case, the tides are going to try and circularize the orbit, make the obliquities upright. It's basically 0-degree obliquity. But the perturbations between the planets are going to try and cause those eccentricities and obliquities to stay away from zero. So this is the sort of competition that is going on in this system. Initially, the tidal heating in this system is absolutely enormous. So that's why I've kind of drawn them as IOs here. Those arrows are meant to represent obliquity. Lion simulated this system for 7 billion years, which is about the estimated age of the system. And they found this very curious result, namely that the inner planet, but both planets' eccentricities go to zero. They basically circularize to a very small level where there's basically no tidal heating. The inner planet's obliquity does go to zero, or very close. So yeah, I'll show you the plot in a second. But the outer planet, its obliquity can actually stay quite large. And it turns out that the tidal heating from the obliquity can actually be significant in this case. And here's sort of the summary plot from Lion's paper, where the top shows you the final obliquities of the system. So the inner planet has a pretty large peak at very small values, much less than 1 degree. But you can see that the outer planet has this pretty wide probability of anywhere between sort of 3 and 30 degrees of obliquity are pretty likely. And that has important implications for the interior. So the inner planet, it has almost negligible tidal heating, but the outer planet, it might look like Io. So it's kind of a curious situation where you could have a system where the inner planet looks like the Earth and the outer planet looks like Io. These results are coming to a publication near you soon. We're almost done submitting it. And the other point to make, of course, is that this outer planet then also goes through a day-night cycle, at least for part of its orbit. Basically, it's a polar day on these planets. All right, I've given you the fire hose of this planet, this figure. I hope I have convinced you that indeed all the different parts of this diagram are relevant for planetary habitability. Now, what I didn't tell you though, but probably most of you already know, is that all these results are generated with the same piece of code, a single executable that we call vPlanet. And if you were here in person, maybe you picked up a sticker. If you didn't, maybe you picked one up on your way out. But this is, and you can see it right here on my computer here, right? So this is a code we've been working on for many, many years. I think I first compiled it in 2014, and these students that I've been talking about have been working on this for years. And so basically you can perform all of these different simulations with this one executable. And you can obviously download it. Feel free to talk to me if you'd like to try it. But there it is, that's on the VPL's GitHub site. All right, so that was part one. Don't worry, part two is much shorter. But I want to now shift gears and talk about how we can actually get about trying to calculate probabilities of habitable conditions on exoplanets. So in addition to vPlanet, we've been working on this code we call Alibi. And this is led by Jessica Berkey, who's not in the AB program. She's part of the eScience Institute here. But she's been working to basically develop a machine learning model to develop posteriors in a Bayesian way. And I'm not going to go through all of these details here. If you're really excited about machine learning and Bayesian statistics, you could probably follow your way through those lines of text up there. I just kind of want to skip ahead to the main result here. So this on the left is a corner plot. Probably a lot of you have seen this before. And it's basically looking at a simulation of the XUV evolution of TRAPPIST-1, which we talked about earlier is really important for this longevity of water on planetary systems, or planets, excuse me. And this is TRAPPIST-1. And the black curves and shading represent results from a code called MC, which is an industry standard that's been around for like 10 years. And then the blue is from this Alibi code that use machine learning. And what I point out here, right, is that Alibi generated those results 1,000 times faster than MC. Now, it's not quite as simple as that because there was some effort to, this was in development, so it took us a while to get there. But if you just press enter, after you've done all that work, right, MC requires 1,000 times more resources than Alibi. So it's a pretty impressive tool. It's still a bit of a work in progress, but if you're interested in more about this, please find me, after the talk or sometime whenever. I live here, so just come and chat. I'm happy to talk about it. So the final step then is to kind of take those XUV parameters and try and estimate the probability that there's water on those planets today. And this is work that's being led by Megan Gianluca. And what Megan has done is basically tried to synthesize the results from Jessica's paper with posteriors for the planets themselves, and then apply the water loss model that I showed you from Laura Amaral, and try and develop these posteriors as probability distributions that there's water on the planets today. So sort of in graphical form, it looks like this, where here, I'm just going to change the colors here, but the red is just the stellar posteriors from the revision from Jessica Berkey's paper from last year. The middle here is the posteriors from Eric Egel's paper, so quite a gigantic corner plot. And then we applied again, like I said, that model of water loss from Laura Amaral, and it goes back much farther than her. And then the results look something like this, where basically we're now looking at the amount of water and oxygen in the planets as a function of their initial water content, which is unknown. So basically what Megan does is she simulates at each of these initial amounts of water and then calculates what's the likelihood of each individual amount of water that's left after 7 billion years. So after all this evolution has occurred. You can see there's that dashed line, which is desiccation. So that's where all the water is lost under all circumstances. But then you can see that there's the best fit line, and then there's some shading that represents the uncertainties. And so basically what we can say from this these simulations is that if the planets form with less than 3, maybe as much as less than 5 terrestrial oceans, then they're desiccated today, at least the ones in the habitable zone. I should be clear about that. This is just worrying about E, F, and G. And we can now quantify that, right? We can say that it seems likely that planet E lost around 8 plus or minus 1 Earth oceans of water, and you can read the numbers there, 5 and 3 and 1 or so with some uncertainties. So that's some pretty tight error bars, and that should make you question these results, and you should, because right? This is a really simplified model. What I've just shown you here is really more of a proof of concept than anything else. Just that it is possible to take some of these models together. And again, I think Josh has done great work looking at similar kinds of projects. So we're just kind of doing it in different ways and kind of coming to similar conclusions that you are able to lose a lot of water on these planets, and that it is possible to quantify it using modern statistical methods. The last point I want to make, and this will be really fast, is just that we've also been working to try and engage the global community with these kinds of problems, because I think the search for life in the universe is of interest to almost everybody. But there's a lot of universities out there that don't have access to powerful telescopes or cutting edge laboratory equipment, but they still have people that probably want to work on this problem of looking for life in the universe. And all of them do have computers, right? All of them have computers either at home or at the university. And so we have started to try and engage people by running workshops where people teach, by the students, the co-developers. We all engage these students. We just had one in September. It was attended by about 50 people from over 20 countries and 5 continents. And they all came to 2 days of lectures. And I'm happy to say that after, and I guess I should have mentioned, yes, this time we looked at this new planetary system called LP890-9. You don't have to worry about the name of it too much, but it is a 0.09 solar mass star with orbited by 2 planets. One of them is in the habitable zone. It was just announced the week before the workshop, but I had advance warning, so I knew we'd be working on it. And within about a week, these different students, with a little bit of help from us, were able to generate all these plots looking at these different kind of aspects of the evolution of this system. So those tools are available, and I think that they're pretty well, I don't know, I was going to say user friendly. At least you can use them with a little bit of help. All right, so that's all I had. I'm going to leave the summary up here because I'm just about out of time. So thanks very much, and I'm happy to answer any questions you have.
Okay, questions for Rory? Okay, well, I have a question.
All right, yes, please.
So 90 degrees obliquity, that's how robust is that? Because I mean, when we look at the solar system, we see Uranus, but all of the other planets don't have a 90-degree obliquity. Now, admittedly, they've evolved, but Mercury's upright, Jupiter's upright, Venus is upright, it's flipped. Yeah. And then the other ones are like close to 20 degrees roughly, or 20 something. So why? This is obviously not what you see in the solar system. Right. So how good is that?
Yep, great question. Were you the referee for that paper? Because the referee hammered us on that point too. But
because I'm
yeah, right, exactly. No, but this is a question that comes up a lot. So every study of planet formation finds that 90 degrees is favored. And the reason why is that when you think about the most likely impact angle of a
45
planet,
degrees.
well, it's going to be edge on. Okay. Right. You're most likely to have an edge on collision that spins up the planet and just basically puts it into whatever the plane of the impact was. And that tends to isotropize, so to speak, the rotational axes of these planets. So it's basically just the collisions basically create a random walk that basically favors this 90-degree obliquity feature that we see. So in our solar system, right, Mercury is affected by tides, and so its obliquity is not 90 degrees. Same with Venus. Earth is controlled by the moon, but presumably its obliquity was somewhere near where it is today.
Mars is 25 degrees.
And Mars is 25 degrees, but it's been all over the place since the beginning of time. The outer planets, of course, they form in a kind of a different way, where they accrete gas from their protoplanetary nebula, and so they inherit the angular momentum vector of the protoplanetary disk. So they have a different formation process. But even then,
so you're talking about rocky worlds.
Yeah, so
specifically.
I should have said, I should have clarified that it was rocky worlds. Yes, that was the point of confusion there. Yeah. So but even Uranus is still tipped over on its side. So clearly a collision, or at least probably a collision, knocked it over as well.
Right. Okay. Other questions? Nick.
Just in very broad strokes, how does machine learning help you do Bayesian inference?
Yeah. So the question is, how does machine learning help you do Bayesian inference? So generally, processes like MCMC, they, as you know, they do this random walk through the parameter space and trying to then figure out where is the high likelihood space. The machine learning process, and I guess I can go back here, and it might help to see the text here. So what the way the machine learning helps, it helps when you have a forward model like VPlanet that takes more than about 1/10 of a second to run and calculate a likelihood for. And in that case, when that is the case, you can then use machine learning to derive basically what we call a surrogate model, but it's basically this matrix of elements that basically describe the features of the model. And that can be evaluated in like 10 milliseconds. Okay, and so by deriving this surrogate model, you basically are able to generate the posteriors with the surrogate model very quickly. The downside there is that you have to build the surrogate model, which we do through Gaussian processes, which takes some time. And then you have to iterate over time until basically your posteriors converge. So what Alibi does is it basically goes through a certain number of steps. And we have this convergence criteria that we set up that's basically once the posterior varies by less than something like 1% over 3 consecutive trials, then we say it's converged. So it's basic. So the real advantage. So that, and I guess the other point too is that when we do this machine learning method, we still have to perform VPlanet simulations to get the truth, right? To get the truth of what that evaluation forward model is going to say. But we're able to, but through the Gaussian processes, you can basically at every point in the parameter space, you can say, this is what I think the code will say, this is what I think the likelihood is, and this is my uncertainty in what I think the likelihood is. And so then what the Alibi does is it basically identifies points in space for which the likelihood is high, but the uncertainty is large, meaning that the sort of the bang for the buck for performing a VPlanet simulation in that space is really high because it thinks that that's going to be a point of high likelihood, and then it can sort of nail down those uncertainties and say, okay, that's the truth. And if it is high uncertainty, then it really knows it's on the right path. And if it's not, then it knows really needs to look somewhere totally different. So as opposed to that sort of random walk of MCMC, you sort of intelligently sample the parameter space to find the where the high likelihood is. That all right? Good.
Yep,
So I have a questions. This is more about the project management or software engineering.
Okay.
In my experience working with Earth models, like the complex one, often it's quite complicated. There are lots of different components, and many collaborators are working on the same project. And sometimes it can be frustrating because when you correct something, say in the interior, it may mess up like atmospheric scales, like in your model. So I just want to know if you have any insights into like how you manage this project so that everyone can contribute at the same time while you can sustain certain level of model reliabilities.
Yeah, great question. So for those of you online, the question is, how do we sort of maintain the software in a way that, and I'm paraphrasing here, so just correct me if I'm wrong, but basically maintain the software in a way that it can be used by many people, that and that work that is done isn't destroyed later. Just how do we kind of maintain the software given its complexity? Is that basically right? Yeah. So this is something we work on very hard. And so there's a few things that we do, right? So we have a lot of documentation to begin with, right? So I mean, we try to explain a lot of what the code is doing, but I think the real thing that really makes this sustainable is that we use what's called continuous integration or unit tests. Basically, it's both of them. So the code is on GitHub. We take advantage of GitHub's software engineering applications, so GitHub Actions. And so what this does is that we basically, at every time we try and merge a change into the main branch, we perform over 13,000 unit tests. So basically all the code maybe I should say all of the code, but a lot of the code that has already been developed and tested and published and peer reviewed, we basically then go through and write a unit test that basically tests the output of all the different parameters. Maybe not all, again, not all of them. It's still a work in progress, right? It's hard to do this on the shoestring budget, but basically we test we test over 13,000 calculations at every test, at every merge. And so that maintains that ensures that any new addition to the code doesn't overwrite and break previous functionality. I mean, and it's really important, and I don't know how we could do it without it. There's other features too. I mean, we build wheels for PyPy, and yeah, I don't know. I'm happy to talk about that with you at length, because and I really want to thank Rodrigo Luger for a lot of that work too. But this is something that we take really seriously. And beyond that, I wrote a code of conduct for the code. So basically trying to outline how we should interact as we try and work through problems and contribute to the code. So I tried to put all that stuff up front. And so at this point, it's still kind of early days in it, and it's mainly just colleagues and graduate students, and we can all talk together. But it might be the case that in the future, we're trying to plan for the future where this is a general purpose tool and people use it whenever they find a new system. They might want to run some planet simulations, and the hope is that they can trust that, trust the code because of all this work we've done. And then we've also worked really hard to make the user interface, the API, very user friendly. So like the inputs all have they have unique names. And one thing I didn't talk about is, right, I think the killer app of ePlanet is that you don't have to recompile the code or anything like that. It's one code that does it all. And so you just have to sort of name the modules or the physics you want to use, and then you can use it. So it's also, I think, a nice pedagogical tool in that if you're interested in this problem and you learn how to do like kind of your thing, like climates, then you've learned the semantics and the framework, and you can start to think about, I want to add in orbital dynamics, or I want to add in cellular evolution, and that whole the syntax is the same, and so that hopefully also it makes people feel that they actually know what they're doing. But I mean, at the end of the day, right, it's still a piece of code that people have to figure out how to use and and trust it for themselves if they're going to try and use it for publications. But yeah, done a lot of work on that. And so happy to talk about that with you more if you have any more questions or want to discuss it some more.
Okay, are there any burning questions online? If not, let's thank Rory once again.
Thank you.